It's around 4,000 to 5,000 kilometers across. It's quite big. And before I go to the maximum ice thickness, I want to show the main areas. So Antarctica, usually we will divide it into 3 parts. East Antarctica, when we call it, this whole region, we call it the West Antarctica, and I'll talk about West Antarctica quite a bit in this talk. So it's good to get used to the names. And then that part is Antarctic Peninsula. It's a really beautiful place. I have flown over Antarctic Peninsula. It's just this amazing, beautiful set of glaciers going out into the ocean. It's really, really beautiful. And I'll also be talking about Thwaites Glacier. So for this talk, if you have registered for the Lamont and you got the Lamont activity, the package, we asked you to, we had included the Thwaites Glacier papercraft with it. And I hope that many of you would have gotten it and would have designed your own Thwaites Glacier, but if not, I'll just show my version of it and we can talk about it. So what is Thwaites? So this is Thwaites Glacier, and that package included the glacier that was included in it was Thwaites Glacier, and I will talk about Thwaites Glacier later on, but it is located in this region. It's one of the largest and the fastest moving glacier, and also the fastest changing glacier in West Antarctica. Actually, all of Antarctica, it's a really big and important glacier. Okay, so maximum ice thickness is around 4,800 meters. So if you think that an average human being is 1.75 meters, I'll let you do the math. You can see how thick the ice is, and you stack one adult on top of each other's head, and you'll see that that's how big, that's how thick the ice is. And in my calculation is more than 2,800 adult human beings that we will need to stack up to measure all that, the thick ice. Average thickness, so that's the maximum ice thickness I talked about. The average thickness is around 2,500 meters. And all of Antarctica contains 60 meters of sea level equivalent frozen into it. And so it's not surprising that 90% of the world's ice and 70% of the world's fresh water is stored in Antarctica. So this gives you an idea of how big and vast Antarctica is. And now we'll have some fun with the names. Just like your house is located in a particular locality, you have street names, you have names for states, you have names for villages. We have some interesting names for East Antarctica, and this map is available on the internet. So if you are curious, you can go and look at the different names and the interesting people and places that they represent. You can learn a lot about the history of Antarctica by just going through this name and figuring out why a particular place was named in a certain way. Okay, so another thing to remember is, again, I will reiterate that this is East Antarctica, this part is West Antarctica, Thwaites over here that I'll talk about is here, and then that is called the Antarctic Peninsula. It is surrounded on all sides by the Southern Ocean, and the ocean also has different seas, and they have different names. So there is Amundsen Sea, there is Ross Sea, then there is Weddell Sea. So it's fun to just look at these names and figure out who are the people that they were named after. It's just a very important part of Antarctic history. Okay, now that we know that Antarctica is really big and it's important, it's worth, isn't it, to spend some time learning about it. So how this talk is structured, it is a STEAM session, which means that I will include not only science, but also a little bit of art into it, and it will have photographs from my fieldwork. So in the first part, we'll understand Antarctic ice sheet, how it moves, how it flows, and how it loses mass and changes. In the second part, I'll share my field photographs and artwork that are used to illustrate some of the processes that I'll talk about. And then we'll talk about sea level rise. And in the last part, we'll just touch upon the Thwaites Glacier, how it's one of the largest and the fastest changing glaciers in Antarctica and why we should learn about it. Okay, so Antarctica is made up of ice sheets or mountain glaciers. They're all made up of compacted and densified snow. It's kind of the same. It's the same snow that you play with in winter. If you have snow in your area or from where you're tuning in the winter, you would have played with the snowman, or you would have played with the snowball. It's the same snow that is in these ice sheets and mountain glaciers. Except that in our regions where we live, the snow eventually melts. But Antarctica is very cold, and in most places, the snow hasn't melted. And for millions of years, it has not melted. So what is the snow? We need to know how ice sheets form. So let's start with the snowball. What is a snowball? Basically, you pick up a lump of snow from the ground, you take it in your hands, and then you compact it to make it a snowball. What you essentially do is you're applying pressure such that you are driving out all of the air that is contained within the snowflakes, in between the snowflakes, with the pressure and with the temperature. You are actually compacting it such that the grains coalesce, compacts, takes a shape that you can make a round out of it, and it holds its shape, so you can throw around and you can play with it. Like I said, ice sheets form from millions of years of snow accumulation. In the same way that you compact snow, it does it by these millions of years of snow accumulation, but the snow compacts under its own weight. And so it's not surprising that the ice sheet forms by layers and layers of snow. So you can actually see these layers. I work on radars where I study how the internal layers of the ice sheet, how the ice sheet also looks, its internal structure. So this is exactly how an ice sheet will look like from decades and centuries and millions of years of accumulation. And this is a schematic of showing how the ice will start moving. Okay, the ice sheets flow, it's not stationary. So these compacted layers, they deform and then they start flowing because of gravity. So this is, like I said, this is a schematic. This is not a representative of an ice sheet. This ice starts over here and then it starts flowing. And these are the mountains that they're based on. And some of them, they flow out into the ocean. I'll talk about that quite a bit in the next few slides. So Antarctica, that's the ice sheet. And if you were to peel off the ice, you would find that in most places it is grounded, that is sitting on bedrock, just like the ground outside or where you're standing. So it is grounded, we call it the grounded ice. And then like I showed, some parts of it float out they move and they float out into the ocean. So the primary colors over here demonstrate the areas where the ice sheet is floating. So there is quite a bit parts of it where the ice sheet goes floating, and these are called ice shelves. And ice shelves are important. They're already floating, so they don't contribute too much to the sea level rise in a way that we would think, but they are used for holding back this huge amounts of grounded ice. They kind of apply back pressure, and then they hold the grounded ice from flowing too fast out into the ocean. That is why the ice shelves, it's important to know the ice shelves, and that's their purpose. And I said that the ice moves. So every bit of it is flowing at different speeds. And this figure shows, this is an actual data from, you can Google NASA measures and you'll find this map. So here is the velocity scale, and the reddish to yellow are slow flowing glaciers, slow flowing ice moving. So these are regions that are flowing really slow. And then the pink and red are ice that is moving fast. So towards the coast, and this is ocean surrounding Antarctica. So towards the coast, the ice starts moving really fast. And I talked about Thwaites Glacier. It's one of the fastest moving. Look at how its color is really red over here. So it's one of the really fast moving glaciers in all of Antarctica. And it's also huge. It's a big catchment, and I'll show it later. Okay, so before I go on to this, I'll pause my presentation for a bit so I can talk about papercraft.
Okay. Indrani, before you do that, we did have a quick question here when you were talking about the ground. So basically when you were saying, when you take away the ice, is the ground grounded ice, is that cold or is that more? So yeah, that's a good question.
It's a very good question. Yeah. And I'm not I'm not a, what do you say, a geologist who studies the ground, but I know that it's very old. I know that it's old, and old things are colder. So it is cold. Yes.
Great, thank you.
And so this is the paper craft that you would have received in your mailbox. And even if you haven't, this is a nice way to just look at it. So this is my version of it. I am sure most of you have done a better job than I did, just because, and some of you may have even colored it. I had just too many choices of coloring this. So this is the glacier, the Thwaites Glacier that I talked about. And it sits on the ground. So the ground over here that Cassie just asked me, that's the ground. I don't know if you can see it. Yeah, that's the ground. And that is the ice sheet moving. And this is the front part is the ocean. I don't have the iceberg that came with it because I don't attach iceberg to it. It is somewhere there. And then you see that this is called, this part, which is going out into the ocean, is called the cabin front. It's not, I can't bring out the contrast in the camera. So that's the cabin front. And there used to be an iceberg over here, which I have not attached. With the ocean, there are so many choices. Even the ocean is blue, we know that. Ocean has different shades. If you Google ocean color, you will find that there are many things which color the ocean. And one of them is phytoplankton. And then there will also be glacier sediments, plumes, things like that, which color the ocean in different shades of. You can Google and see how many shades you can get with these organisms or mechanisms that from the glacier sediments, you can color them with different colors. Okay, so we'll go back to the presentation again. And Thwaites Glacier, so I will talk about it again towards the end. Share screen. So, and I'm an airborne geophysicist. I survey the ice sheet. I use instruments which are fitted on the plane. So this is an aircraft that I used to frequently fly on, this NASA's DC-8, and these are some of the pictures that I took from the plane's window. Our instruments are usually located within the belly of the aircraft or on the wings. They constitute of airborne laser altimeters, ice penetrating radars. There are gravimeters, magnetometers, cameras on board. And these are some of the pictures from Antarctic Peninsula I talked about before. Such a beautiful place, and you can see what I was talking about. So this is an outlet glacier flowing out into the ocean. That's the ocean. That's the cabin front I showed in the paper craft. So we understood how an ice kind of floats on the ocean. And this is another aircraft that I have flown in and collected data. This is icepod, and this is at Le Mans. And this is something that you would have seen today if you had come to Le Mans for the open house. That's the icepod. We still have it in the lab. So next year, maybe when everything opens up, you can come and take a look at it. And these are big mountains. So Antarctica is also fringed by big mountains, tall mountains. And because I fly these aircrafts, they do not fly at commercial heights. They fly 500 to 600 meters from the surface. I fly very close to tall mountains, and you can see this is so beautiful. This is my first time in McMurdo. So when we go to Antarctica, we'll first go to McMurdo, that is the US base, and then we fly out to different regions and do our work and come back to McMurdo to fly back home. This is my first time in Antarctica. You can see this is our team. We are very excited about for some of us, it was the first time as well. So we are very excited about getting our feet on Antarctica. We flew on this New York Air National Guard airplanes to McMurdo. That's how the inside of the plane looks like. And then we work in tents. Like this is one of typical tents that we do our field work in. That's McMurdo. Our living quarters were here. There is a cafeteria. There's everything in McMurdo, including a post office, churches, and then you can see some steep hiking areas. We cannot go everywhere, but there are some areas we can we can go, and this is the ice shelf and the sea ice that I talked about. I haven't talked about sea ice, it's frozen seawater, but that's not, I will not be talking about sea ice much today. And this is an active volcano in Antarctica. It's Mount Erebus. It's just such a beautiful volcano. Everything about Antarctica is beautiful. I can't stop talking about it. So it doesn't spew lava or magma, but it is always spewing out water vapor and some gases. So it looks like it has a crown on, sitting on top of its head, a white crown. This is how a typical day in Antarctica looks like, beautiful and bright, but there are also snowy days and stormy days. This is just start of a snowstorm in Antarctica. And if the storm intensifies, we do not go out of our quarters. And this is me just looking outside my tent. This is one of my artwork. And I work on blowing snow, so I like this kind of weather. I like to just stand outside when it is relatively safe to do so. And I like to ponder about the early explorers. Now everything is so easy, everything is mapped, but in those days when nothing was mapped, it would have been, they would have faced so many challenges in navigating, not knowing where they're going. Crevasses, these are dangerous. This is a photograph taken from air and they look nice, but we don't go near any crevasses ever. These are restricted areas and dangerous. Most of Antarctica looks really flat and looks like nothing much is happening, but we know now that it's moving and it's changing. And who lives there? Only the cutest animals on the planet. The penguins, everybody loves penguins. This is one of my, I couldn't help it. I had to draw penguins. And then that's a baby seal. He was born when I was there in Antarctica. It was such a nice, it looks like he's smiling. He's very happy to see, very curious to see the world. Okay, so now we know about the ice in Antarctica. Let's talk about the ocean a little bit. And actually, we will talk about why Antarctica is changing so much, so rapidly. It's mostly because of the ocean. Now, this is an actual data. It's from this published work, Pritchett's. So this is ice. Those are the ice shelves that I just showed. And then we'll not go into many details. This is the ocean, and this shows the ocean temperature. So just remember one thing, pink is warm and will cause melting. So we saw that, and I'll talk about it, that the ice shelf floats onto the ocean. So it is in direct contact with the ocean. So pink is warm and blue is cold, okay? And then Thwaites Glacier that we talked about here is actually located very close to the pink ocean, which is warm. And here we'll learn the important mechanisms by which Antarctica loses mass. So the ice shelves, they are the floating extensions I just talked about. They float out into the ocean. This is the ground. And so the ocean, if the ocean is warm and it's the pink ocean that I just showed, then it will melt the ice from the bottom. Oops. It will melt the ice from the bottom. So this is what is happening. The ice is kind of thinning. If you notice, it's getting thinner and it's also retreating further inland. It's becoming thinner. When something becomes thin, it's usually, it can be easily broken. So that's how now you can see that there are few icebergs over here, which are broken pieces of ice. And then now you see there are more icebergs. So it just kind of melts from the bottom and breaks. And I also said that the ice shelves are important because they hold back the continental ice. They kind of makes it move a little bit slower. And if it thins, if the ice shelf thins and it breaks, then more ice from the interior flows out faster into the ocean. And those are the main ways that Antarctica loses mass. Okay, like I said, if more ice flows into the ocean, it causes increase in sea level. So here, just for demonstration, I have this woman who is 100 years old. Her name is Tula. And since the day that she was born until today, the sea level has risen to here. So that is around, in the past 120 years, the sea level has risen by 6 to 9 inches. And this sea level rise is not linear, which means that in another 100 years, we may not see a doubling. We may see a little bit more. The water may not be up to her sweaters. It might be somewhere else, higher. And Antarctica, during 1992 to 2017, has contributed to around 6 to 8 millimeters of sea level rise. That's the cumulative. So it's in, the contribution is in millimeters. So, you know. Okay, so this is the almost the last part, and as promised, we'll talk about Thwaites Glacier. So this is one of the field photographs from the field. This is the calving front, the ice front of Thwaites Glacier. It's a very beautiful photograph. And this is where Thwaites is located. So I've been talking about Thwaites, I've been introducing it throughout the talk. But here you can see how big it is compared to, you know, this is all of Antarctica. This is really big. So Thwaites Glacier is almost as large as the state of Florida. And it's one of the most unstable glaciers in Antarctica. It's one of the fastest moving. I showed the velocity map. We saw that how fast it was moving, and it's also really fast changing. It contains about 0.6 meters of sea level equivalent. So if you think of that 100-year woman I talked about, and if she is 1.7ish meters tall, then it's roughly, you know, if Thwaites Glacier disintegrates, it will increase. So you can imagine how that it's roughly 1/3 almost of sea level rise equivalent, okay? But just as a word of caution, it is changing very rapidly, but we do not expect it to collapse immediately. That's the one thing we have to keep in mind. It will take centuries for it to collapse totally, but it will keep on contributing to sea level rise, and we don't want that. It is so important that NSF and NERC, so NSF is the US funding agency and NERC is the UK funding agency, they have joined hands to fund 8 projects we call the International Thwaites Glacier Collaboration to monitor the ice, the glacier, and I'm part of one of the teams. So we are using all sorts of measurements available and ice sheet models. So we have ice cores that drill into the ice and measure how the climate conditions have changed and how it's going to change. Then we do airborne measurements. I specialize in those. So we have radars, we take lidars, and there are several other instruments like gravimeters, magnetometers. Those are the airborne suite. And then we also use a lot of ground measurements. So people tag their instruments in vehicles like this and then go around traversing on the ground, on the ice, and then measure different changes. There are shipborne measurements, like ocean temperature, salinity, those kind of things. And then there is also submarines are used to go underneath the ice shelves where the ship cannot go. And then of course you can't see it because it's too dark. There are satellite measurements. There are some very important satellites that have been launched in the past couple of years that are starting to look at giving us higher resolution data and more frequent data, but really observation through satellites has gone back into decades. We've been doing this for a long time. Okay, to conclude, so we learned today how big it is. It's a really big ice sheet, and it's important. It contains thick ice and has 60 meters of sea level equivalent stored into it. We talked about the ocean temperatures. The ocean around some parts of Antarctica, including Thwaites, is warm, this pink color, and blue color is colder. And then we talked about how Antarctica loses mass. It's through iceberg calving, through melting of the bottom of the ice shelf. And also when ice shelf is damaged, it brings out, it's thin and it provides less buttressing to the grounded ice, and the grounded ice starts moving faster out into the ocean, causing more melt. So those are the main ways that Antarctica loses mass. And then we talked about Thwaites and our international collaboration to study the Thwaites glacier change. And with that, I come to the end of this talk. Thank you for being with me.
Great, thank you, Indrani. And I should say, I don't know if this was clear at the beginning, but all of the drawings that you saw throughout the session through Indrani's slides were actually done by her. And so I think they're really great ways of communicating the science, but through artwork. And we have quite a few great questions. So I'd love to get to those. So we'll go back to the beginning. And Lincoln asked, how cold can Antarctica be?
Antarctica can be really cold. So when I was there, the average temperature in the summer, I was there during the summer months. The average temperature is minus 20 Fahrenheit, and then it can get really cold. There are some parts of Antarctica in the winter can get down to minus 80, or even colder has been observed. So minus 120. It's really cold. It's uncomfortably cold.
Okay, got it. Thank you. When you first went down to Antarctica, so your first trip down there, was it summer? And I think typically, if you could talk about what months are the best months that you go to do research, and what the seasons are like there, that'd be great.
Yeah. The first time I went to Antarctica, or scientists usually go to Antarctica during the summer months, because that's when you have the daylight and you can do your research. You can deploy your instruments. You can fly around and do your research. There are the logistics people. Some of them, they winter over because they have to maintain the bases, McMurdo, the facility. So they winter over. There are also sometimes a few scientists whose research requires them to stay throughout the year. Mine doesn't, because I need to have daylight. I need to see where I'm going, and I need to see, it's airborne. So it's also sometimes very difficult to fly an airplane in the night and nighttime to do a survey. So in Antarctica, what happens is, if it is not summer, during the winter, it's 24 hours. There is no sunlight. Okay, so it's complete dark. So that's how the seasons look like. It's cold and colder.
I like that. We should have a bumper sticker that says Antarctica.
And we want it to remain
Yeah.
cold. Yeah, that's in our benefit, that it stays cold.
Okay. Yeah. Great. Thank you. And the next question is, can people go to Antarctica if you're not a scientist?
That's a good question. I get that quite a bit. Tourists go to Antarctica. You might notice you can take ships and go to Antarctica, but McMurdo also have a lot of support staff that are there. And there, I have seen students, graduate students, working in Antarctica just to get an exposure of how, there are also management students who sometimes go to Antarctica to work in McMurdo, the US base. So there are different ways of going to Antarctica. Some of them volunteer to go to Antarctica, and they're mostly students. And then also McMurdo, or any kind of support base, needs a lot of personnel to maintain. And so, yeah, it's also a paid job for many of them. They go to Antarctica on a job to help with the research facility. They upkeep, they look after everything that's going on there.
Yeah.
So apart from being scientists, there are all these people. So our science requires a lot of support from other people. And that's how people get employed to look after or to maintain the region. And then I have also, like I said, I have seen students go there to get experience. I have seen interns. And then there's a third category, is the tourist. I can't think of anything else. Over to you, Cassie.
So it's funny because my mother-in-law said, "Oh, you should, if you're giving a talk about Antarctica, she actually knows someone who is a chef, and her specialty is baking bread, and she teaches at a small college in Maine, but she has been to Antarctica, and she was part of the kitchen staff team, I believe, at McMurdo, and she had to basically relearn how to make all her bread because the conditions were just so different than what she has back in her kitchen. So it's not, I think it's not just scientists. I think I think your example of McMurdo, and that it has a lot of support staff to keep it open and going all year round. And there
are doctors. Yeah, there
exactly.
There are doctors. There is a post office, and then there is also clergy. There is a church I mentioned.
Oh, wow. Okay. Yeah.
Not that it's like, not that I've been inside that, because during the day I'm constantly working, and it's just something that I looked inside, and I haven't seen what is inside, how the church will look like inside, but there is clergy. And
Okay.
there was a barber shop. That's fantastic. There's, of course, the big cafeteria. There are so many. It's just like a small township.
Yeah, that's great. Yeah, thank you. And we have a question about what inspired you to learn about, the person said Arctic, but I assume Antarctica, or just perhaps ice in general, and what's happening with ice. Why are you so interested in learning more about it?
So I started my career as a physics major, and I did particle physics. So it's really, really far away from any of the things that I work on now. And I did my PhD in atmospheric dynamics. So that's what introduced me to climate dynamics. And then I took a job which was in the Himalayas. I was mainly interested in climate and climate dynamics, not particularly for ice, but it was more the atmospheric circulation. And my job took me to Himalayas. I saw the glaciers and I thought I could work on them because they are similar principles and they are beautiful. So, and I have this adventure because I also like to paint. So I see beauty in things, it motivates me. So I think that a sense of adventure, one has to be adventurous in order to study Antarctica. There is no other way. I think all of us have been drawn to the adventure and the beauty, all of us who work on Antarctica, and also the climate impact of it. So I thought that with my experience, with my knowledge and background, I could contribute to this area. And so I applied for a postdoctoral at the University of Alaska Fairbanks, and that's where everything started. And then I found my way to Alaska. I have worked a lot on Alaskan glaciers. I have lived in Alaska for a couple of years, and before I came to New York. And then my travels have taken me to Antarctica and Greenland. I have been very fortunate seeing those places. But I would say the motivation behind it was the climate. Really.
Okay.
All throughout my background, starting from PhD, the common thing that has remained with me is the climate dynamics.
Okay. Fantastic. Thank you. We have a couple of questions about animals, and you showed us some very adorable animals and penguins, and our viewers wanted to know if you've personally come up close or met seals and penguins, and curious how they've responded, and how many of them have you seen at once? Is it a lot, or yeah?
Well, we're in Antarctica, these species are protected. We are not allowed to come very close to them. So you have to maintain a distance, a very large distance, 50 meters or so. So we can only observe them from far away. My camera has this big telephoto lens attached to it. That's how I took pictures of the baby with this close up smiling. It's not like I was standing next to it, but there are a lot of seals in McMurdo. So if you go there, and you're peering down onto the ice shelf, you can't miss them. And they like to live together, they cluster together. So in a go, you would see 20, 50 seals. And then when we go there, it's the summer. That's when usually the babies come. So you also get a lot of baby seals. For penguins, I have in my lifetime just seen one penguin, and that also a penguin which was kind of wandering around, figuring things out, I think. But we are not allowed to go close to any rookery. We are not allowed to fly over them. We cannot, because the noise of the aircraft disturbs them, and we don't want to change any of their natural habitat. They're so fragile. So penguins have been, I have just seen one, but I have seen a lot of seals.
Okay, great. Thank you. We have a question about how much does it snow in Antarctica, and is snowfall changing at all?
Yeah, that's a great question. So in the interior, in East Antarctica, the snowfall is really low. You'd be surprised. It would be like a few centimeters of snow. It's like the world's largest desert. But if you go to the West Antarctica and towards the coast, the snowfall can be as high as a meter per year, a meter of snow. And then these are rates I'm talking, they're all in meters per year. So it's a total accumulation. What was the question? Is that all, or is the snow changing? Yes.
Is the snowfall changing at all?
Yeah. So in the towards East Antarctica, towards the Weddell Sea side, Ronnie Filchner Ice Shelf. You can Google the name, or you can see it on the map. Towards Dronning Maudlin, we are observing a change in snowfall. So you're seeing a higher rate of snowfall. In other areas, it's hard to it's hard to say whether this is because of climate change or because it's something that's naturally happening, natural variability, we call it, because of large-scale atmospheric phenomena. But definitely there has been evidence that snowfall has increased. At least during the last few years, we have seen higher snowfall rates in parts of East Antarctica. And the theory is if it's getting warmer, it will snow a little bit more than what it is snowing right now.
Okay, great. This is another good question. We have a lot of great questions. Why are crevasses dangerous? So maybe you can maybe talk a little bit about what they are, and can you go near it at all?
The crevasses are dangerous because so you understand that they are cracks in ice. So they're weight shifted like that. If you can see my hands and follow my hands, they usually they will open up and they are deep. If you fall into a crevasse, it takes a lot of effort. It's often dangerous for the other people as well who are trying to rescue you. If you fall into a crevasse, there is almost no hope of getting you back alive. And sometimes it's even difficult to get to you. Usually we will need helicopter rescue or something airborne to pull you out of a crevasse. And because it is cold, so the surface is cold, but the interior of the ice is colder. So the hypothermia sets in really fast. So if somebody is able to rescue you, it has to be within a very short time. Any time longer than this, it's like someone would just freeze. So this is why crevasses are dangerous. I work on crevasses, but I use airborne and I use satellite data, and validation for my work for crevasse regions is really hard for this particular reason. It's inaccessible. It's very difficult to do, and which is why the studying of crevasses is lagging behind a little bit, just because any of the theories that we develop is hard to validate. Yeah, it is difficult and it is dangerous, and we are not allowed to go near crevasses.
Right. Okay. And to kind of follow up on that, because somebody else had asked a question about, so how cold is the water, I guess, around the ice, or that the ice is in?
Yeah, the surface, it would be like, if it is warmer, it will be around 2 degrees centigrades, but it gets a little, so there is a profile. Sometimes it is warmer towards the base, 1.5. That's how cold the water is around. That's the summer temperature. In the winter, it freezes up, so it's ice.
Yeah.
So it's covered mostly in ice. So what I'm talking about right now is the pink water that I showed you. That's around 1.5 to 2 degrees, and that's during the summer temperatures.
Okay, great. And we have a question here from Celia, who's asked, what kind of fuel is used on the equipment that you use to actually, you talk about flying, and does that, for example, the airplanes, and does that actually, add to sort of climate change impacts? And yeah, so good question, Celia. Thank you.
That's a great question, and something that has bothered me and other scientists as well. So when we fly, it is the same aircraft fuel that we would use for flying it.
Those aircrafts in New York Air National Guard flights flying anywhere, right? So it's the commercial fuel, and so our survey does come with a price. Yes, but to observe something, we have to observe how it changes. We do have to understand. We have to take measurements. So we try to maximize the amount of stuff we get done. So we make actually really efficient flight plans. So we like I said, this is not one plane flying with just one instrument. It has multiple instruments into it. And one flight serves the community, the entire community. IceBridge has flown on it. And I am using IceBridge radar data. I use LiDAR data, and scientists all over the world have access to this data. So it's opening up. It's just that one flight. So you look at the cost and the benefits. And hopefully in the future, we'll have better ways of doing it. So we are also looking at drones, but drones, they cannot survey long distances, but we are still trying to develop, scientists and engineers that are trying to develop efficient drones that can do the same thing as an aircraft does. So we are conscientious about it, and we are thinking about reducing our carbon footprint while we do the surveys.
Yeah, no, thank you for that. Important question: is there Wi-Fi in Antarctica?
Yes, there is. Thank goodness.
Is it better than the Wi-Fi that we're using at home to work at home? Probably.
I had no complaints there. It was just the same.
Yeah. Okay, great.
Yeah.
So we are running out of time, and I'm going to have to choose one last question, unfortunately. But if there are additional questions, feel free to email me. I'll put my email in the chat box for everybody. I think this is a nice way to wrap up. Perhaps, what's the longest amount of time that you have spent in Antarctica? It's not just a trip that you go for, a week, because it takes so long to get there. So I'm curious to hear about that.
Yeah, so a field work in Antarctica takes a long time to prepare for it. I have to go through medical procedures. I have to be fit enough to go to Antarctica. So the doctor I have to have physical examination. So it starts longer than that. And then in Antarctica, you just can't go there and come back after your survey is done. The survey itself
is weather dependent. So if it is cloudy, we cannot fly. And the longest I've stayed in Antarctica is October through early December, late December. Yeah. So summer months, there will be a last flight you don't want to miss the last flight out of Antarctica. That's
yeah. Yeah,
I have to get back home. We're stuck for the year.
Yeah. Yeah, exactly. Okay, well, thank you. We're slightly over time, and we do have another session at 4. So I apologize if we did not get to your question. But I've just put my name and email in the chat box. If you're interested in getting one of those paper crafts that Indrani was showing, we still have a couple of packets left, and I've put the link to sign up for one in the chat box as well. Indrani, any last sort of parting words for our viewers?
Yeah, it is such a fragile environment. We work on ice, and you can imagine
in a warming water or a warming climate, how stable is an ice sheet going to be? So I would say the thing that motivated me was climate, and I would like the ice sheets to stay as they are. And so we have to take care, and so as individual, each of us have to make our choices, just that we try to remain green, and we contribute towards the positiveness, to check climate change. So do it in ways you think can have the largest impact. There are many ways of doing it. Think of some innovative ones as well.
All right, that's great. Thank you. And for our viewers, thank you so much for tuning in. If you have any additional questions, feel free to get in touch. Indrani, thank you so much again for sharing some great information, your artwork, and sharing with us your very important work. And thank you for your time.
And very much.
Yeah, thanks everybody. And if you are session at 4 o'clock, if you're interested, Laurel Zaima is actually going to be showing us more about ice. We're continuing our ice theme, and she's going to be making glacier goo for us, and we're going to see how ice actually flows to continue ice, the ideas around ice and how it's changing. So thank you very much, and we'll see you hopefully all at a future session. Indrani, thank you very much. Have a great